Welcome back. Chances are that you use the word subset in everyday speech, and you probably use it correctly. It's one of these concepts where the natural language of the word has stuck with what the logic means as well. But we want to make sure that our logic is really sharp, especially as we start to see that logic changes from one context to another. And so, whenever we write down what a subset is, it should be a journey into some particular logic so prescriptive that eventually we can even compute with it. But to get to the right model, we often benefit from some pictures that help us reason more quickly than, say, a calculation might. So one of these is the Venn diagram. The Venn diagram, we start with drawing some typically geometric shape, something like a rectangle, an oval, circles, it doesn't matter what you describe. And we might label it with the name of the set that is the biggest one we're discussing in the storyline. I'll start with a set A. If I look at the night sky, I see many stars. The bright ones appear right away. Some of them, though, I would have to concentrate on that part in the sky or use a telescope to notice that there's a faint star back here. I like this version of the story because often when we look at a Venn diagram, we forget that this is just an illustration of our data set. We put in a few examples, but we know that there could be many that you haven't actually seen in this picture. If every set is just a geometric shape consisting of stars, then a subset is a constellation of these stars. I'll draw one right here. When we draw constellations in the sky, we often contour them with shapes that have nothing to do with the stars. The shape of the stars doesn't exactly trace out Orion, at least to my eyes, but the intention is still there. The boundary around these stars is meant to say the things inside this count as part of Orion. What I've just described is a subset of stars. This constellation, I'm going to give the name B. It's also common to shade these in. Now let's face facts. Venn diagrams are wonderful to draw and they can be artful, but they often bring into the story things that have nothing to do with what we're really studying. Let's imagine that A is the set of all URLs, every place that we could search on the web, and that B are the malicious URLs, the places that could damage our computer if we visited them. That's not going to be drawn as a constellation that looks like a famous Greek god. So we're adding to the story things that are metaphorical and make us enjoy what we're doing, but they're not going to help us do calculations. If we stand back and see what we're really saying, we're really talking about containment. We have a bigger box and something smaller with all its values contained inside. And if that's all we're saying, then maybe we should create a diagram language that talks just about that relationship. And the Hasse diagrams do exactly that. Hasse diagrams start with the largest things on top. And the smaller they get, they go below. But we don't leave it just there. We try to draw connections between the data we have and the data that we're looking at. This single line doesn't need to be an arrow because we always use the convention that the larger is above the smaller. So therefore we save on some chalk. Of course, if all we're doing is talking about one subset B, then this picture is maybe more than we need to visualize it. Where this comes in handy is when we have 2, 3, or many types of subsets. So let's add to our picture, both in the Venn and the Hasse diagrams. So here I've shaded a constellation C. It's separate from the constellation B, even though it shares some of the stars. What we want to do with this picture is demonstrate the ways that we could possibly share some of the subset data. Let's see if we can do the same thing with the Hasse diagram. And notice I've also repositioned the values of B and C. To take into account the relative size, C is slightly smaller than B, so it goes further down in my picture. And I've moved them to the side so I can draw lines between them. Now the missing in the Hasse diagram is the connection to A. I now see that I have a branching between B and C. But the Hasse diagram and the Venn diagram are both prompting me to think about some new sets, ones I didn't design, ones that are visible in the pictures. For example, I can see that C and B share some constellation stars. They share these points right in the middle. That should get a name. So let's imagine what's a star that's right here. A star that's here is in C and in B. Let's write that out. To say that X is in C and in B is a logical construct. There it is drawn as a logical operator with a wedge in between instead of the simple and. If you look at this notation, you'll see that we're asking if X is in C and if X is in B. We might simplify this notation and create a new set, which is the combination of being in C and in B, and then just ask if X is in that new combined set. We want an operator to combine C and B in a way that looks like our AND operator. The solution is to mimic the same notation, but take away the sharp edge. Instead of the wedge, we now have this upside down rounded wedge. It's called intersection. It's a way of taking a logical operator and creating a new set from it. In the Hasse diagram, we can also draw the intersection. Because B intersects C is contained in B, it should be lower than B. but it's also contained in C, so it should also be lower than C. So that's the right place for B and C. If we add in the missing relationships, we should have lines that go from B intersects C up to B, and from B intersects C up to C. We've now created a picture which captures the concept of these shared stars between the two constellations. But isn't there another set? This was using the logical operator AND. But there are other ways that we can combine data sets. We could combine data sets with an either. Either it's in C or it's in B. When we do an or, we flip this notation and it becomes an upside down wedge or a V. Flipping the and for an or is called a union. We've unioned this constellation with this larger constellation to create a new constellation, which is both of them together. We now have X's in C or X's in B. Notice okay for stars to be in both already. That doesn't count against the union. We have a new notation for the union, which is like the or symbol, but again, rounded off. It also reminds some people that this is U for union. That works in the English language at least. How do we update our Hasse diagram? Our Hasse diagram also has a place to locate the union. The union is containing both B and C. It's the larger of these. So it should move up in our diagram. And there you have it. That's where B union C is. We start to get a different sense for how we compute with our data sets when we draw these pictures. What we're saying is that there might be things that they have in common, places that they overlap, and they might have more data together than individually, their union. All of that, nevertheless, sits inside of the largest place, the set of all the data. What we are trying to do is head towards diagrams that give us a sense for how many different ways we can slice up our data. What's behind all of these, nevertheless, is something that we want to do computationally. So what we're really thinking of is that these various subsets are given by some rule of being in the constellation or not. That means that behind each of these are some predicates. We're in the middle of a study of subsets and sets. In this, we needed to understand properties, the properties that a subset had. So I'll remind you of the scenario. We had client files, and we were looking at whether they had matching zip codes for some particular region. But there could be many other kinds of properties. So here are some examples. When we take any property whatsoever, we like to collect them in one data type. We'll call that prop. The word property makes sense computationally. Mathematicians prefer the phrase proposition. There are plenty of situations where natural language makes it clear what a property is. But to make it computational, we need to turn them into functions. And we did that, for example, in our client list using zip codes. That's our first example up here. We could take a file of our client and ask for the zip code of it. If it matched 43210, we would put a checkbox on it. That checkbox is indicating that the property is satisfied, without giving any bias as to how it was satisfied. It's just a yes-no answer. Notice that leaving a checkbox empty doesn't necessarily mean we know it's false. It just means we don't have evidence that it's true. So this could actually walk the line between both classical and intuitionistic understandings of our data sets. Other things you might ask for could include something like searching URLs. If I type a URL into my browser, it'd be helpful if my browser told me not to go to a malicious website before I accidentally hit yes. So it could ask the question, is the URL a malicious website? And if it can determine that it is, it'll set this marker to check and send me a warning instead. In order to practice this, let's take a simpler model of just numbers. Let's ask if our number is even. We could write this down by writing down all the numbers on a number line. Let's put a few examples up. Once we define a property, we're actually defining it across a number of possible values for those variables, the domain of that function. In this case, if we're using the property that x is even, we could look and say 1 is not even, so we leave it empty. Number 2 is even, we put a check mark there. P of 3 is not even, we don't check it. P of 4 is even, we continue on. If we stand back, what we're doing is we're plotting the function p that starts with an integer and assigns it some proposition. Every single integer gets a proposition. That simply means every single integer has a checkbox, but not every integer gets checked. A function like this is known as a predicate. A predicate simply means that it's a function that could come back with a judgment of true or false, but it has a variable that has to be replaced in order to make that judgment. In this case, we had to replace the value of x with, say, 2 or 3 or 4. Recall we thought of a predicate as a checkbox. For every little star A, we create a test of whether that is or is not in the particular subset. P could correspond to the red constellation. The green constellation could be Q. A star that's right here would have this one checked. But because it's not in the green, it would check the Q. If instead we choose a star that's in the overlap of the green and blue, then we would check them both. We start to see that these checkboxes are actually all we need to do to keep track of the visualizations. The visualizations will give us ideas as scientists of what questions we want to ask, but the ability to track them as just checking off checkboxes gives us a way to do this computationally. We'll have a whole video on the computations of subsets. I encourage you to watch it. What we now need to do is to meld the ideas of ands and ors and other ways to combine different subsets together. In fact, it'd be great if we had one data type that described all subsets at once. Let's see if we can put that on the board. So let's see what it would look like to try to challenge ourselves to look at all subsets in some uniform way. This has the name of a power set. I have over here the Venn diagram for a very small collection of data. I have exactly 5 stars in this universe, and I'm interested in all the constellations that could be made there. So, to start out with, I could have a constellation for every individual star, just one star in there. Let's put that in our Hasse diagram as well. I have 5 separate stars, so I have 5 separate things on my Hasse diagram. Because those only contain one star, they're very low in my Hasse diagram. What's another one that's obvious? The entire collection could be a constellation. 1, 2, 3, 4, 5. That would go at the top of my Hasse diagram. Now let's look at some options in between. Some of the options in between could be to look at pairs. For example, 1 and 2. It's starting to get a bit crowded in our Venn diagram. Let's go to our Hasse diagram and see if it gets any better. You can start to see I'm running out of room, and I haven't even exhausted all pairs. At least it seems more systematic than drawing our circles. First, I started with all the ones that contained a 1, and since there were numbers 1 through 5, I had 4 possible choices: 1, 2, 1, 3, 1, 4, 1, 5. Then I could look at the options that contain a 2. There should be 4 of those as well, but here I've run out of space. The idea, however, starts to feel a little bit repetitive. There should be 4 things that contain 3, 4 things that contain 4, 4 things that contain 5. I'll keep spreading them out. In total, I have quite a few subsets of size 2. Next, we would look at the sets of size 3. In this, for example, we'd have 1, 2, 3, as well as 1, 2, 4, as well as 1, 2, 5, and many more. Before we get carried away, let me go ahead and tell you that most mathematicians would never draw a picture this large. What would you even get out of it? If you look at this, there's too many lines to see a pattern. At some point, we need to let go of visualizations and return to the algebra, the things that we can compute with. So let's try to take the pictures and replace them with formulas that describe the same idea. The key thing I want to return to is the concept of a predicate, checkboxes. For each subset, I simply need to tell you whether you're in or out. So I could give you 5 empty boxes, and you assign whether it's in that predicate or not. These 2 checkboxes are telling me that I'm relating to the sets with the values 1 and 3. It would be this one together with that one. Somebody else could give us a different predicate. This predicate has 3 checked boxes, and therefore it corresponds to a set with 3 things in it. In this case, it's the set 1, 3, and 5. You have the start of a data type that describes all possible subsets. We simply need to describe a function that takes in the values 1 through 5 and assigns them one of these predicate values. So if we stand back to see what we're saying, we're creating a function called the characteristic function. It's the function that tells us whether we are in or out. Each one of them assigns a predicate value. That property can depend on I.
P from A to prop is the type of evidence required. For example, P of n equals n equals 2k. That evidence might not exist. X from A to prop converts evidence into truth. X of 4 is true because it is even. X of 5, you won't ever find that k, so you won't get true by mistake. P from A to prop is the predicate, judge. X from A to prop is the characteristic function, the judgment. Got it? Well, there's always rewind.
So here's the takeaway. The power set of a set is just a new type of data. It's a new data type. It is all the functions from A to a property. An individual subset is associated to one specific function, P from A to properties, where we simply think of the data as all the A's and A's which have a filled-in checkbox for P of A. We might have to wait some time to discover if a checkbox is checked off or not. That's the struggle of computation everywhere. But we take the subset to mean everything that will, in time, be understood to have been checked. This is what bridges the mathematicians and classical logical thinking of subsets with the computational. Until next time. That's how you take care of your chalkboard.